Hello everybody, we're looking at electromagnetic induction and Lenz's law in this video, and we'll analyze it based on the motor principle even rather than just thinking of it as a rule. So video here to watch if you're interested. I'm not just going to play it here, but 9-minute mark till the end to go with electromagnetic induction. So I think the previous video had that same video to watch the first half to do with magnetism. I didn't mention it, I don't think so. But we know, of course, electromagnetism was discovered by Hans Christian Ørsted. Basically found that a needle of a compass would deflect if there was current nearby. So he showed that a steady current produced a steady magnetic field. I suppose I could have underlined both parts, but yeah, steady current and then produce a steady magnetic field. And that's important because often in science things are reversible, right? So you might think the opposite would be true, but he looked for it, realizing that the reverse is often true, and he found that a steady magnetic field does not induce a steady current in a wire. Obviously, there'd be conservation of energy issues there, right? You can't just stick a magnet near a wire and expect electricity to flow forever and power a grid for free, But that was what was found, right? And so he did discover, though, that a moving or a changing magnetic field does produce current in a wire. So moving or changing magnetic field does induce electricity to flow, and that's what electromagnetic induction is. So he developed a generator, and the design of it is used all over the world to this day, which is actually, you'll see later in this lesson, really just the same as a motor, just in reverse, or the opposite order, I should say, not literally just reverse, but reversibility of science kind of thing. So he did investigations. He found that moving a wire through jaws of a stationary magnet would induce electron flow. Moving a bar magnet in and out of a coil of wire induced electron flow. Moving a coil of wire near a stationary magnet induced electron flow. If you think of these two things, they're the same. They're just like relative motion kind of thing, right? It doesn't matter whether the magnet's moving relative to the coil or whether the coil's moving relative to the magnet. The point is there's going to be a changing magnetic field. And so found that current was induced only when the magnetic field in the region of the conductor was changing, right? And that's basically the gist of the story of the law of magnetic induction, or electromagnetic induction, really. So whenever a conductor is in a varying magnetic field for whatever reason, based on whatever kind of relative motion, right, a force is induced on the electrons in the conductor, which causes electric current. Okay, so technically this is Faraday's first law. The second law is to do with the strength of the electric field, the magnetic field, and so on. Yeah, that's what they found. So picture north. I'll show you a video in a second here. And north going in towards a coil, and there's going to be electrons flowing to make current flow. Now, I'm a bit ahead of myself here, actually. I want to jump ahead to Lenz's law, because it'll be to do with this video. I'll have to reorder the slides here. So on top of electromagnetic induction, which he said was, I'm terrible with dates here, 1831, right? And then this person, last name Lenz, came along and studied this some more. Excuse me, pardon me. So Heinrich Lenz in 1835, a little while later, came up with Lenz's law, and he found that, of course, there's an electric current induced in a changing magnetic field, and then realized that electric current creates its own magnetic field. And so Lenz investigated the direction of that magnetic field, and he reasoned, based on the law of conservation of energy, the order that it must be, and I'm actually going to talk about this on the next page. But the direction that magnetic field would logically have to be based on conservation of energy, and I'll go through it here. So he reasoned that a magnetic field here, if it's moved towards an iron ring, it's going to induce a magnetic field, or it's going to change the magnetic field in this area, right? And so, actually, sorry, the first paragraph here is about the fact that the magnetic field to do with this coil could only be to the left or the right. Right? We have our left-hand rule for a coiled conductor. You can have a magnetic field left or right. And so if he brings in a north, then he reasoned that the electron flow, either what do you call this, clockwise or counterclockwise maybe, he reasoned out that you'd have to have electron flow in such a direction that it's going to make a magnetic field that will oppose this change that was coming in. Otherwise, the magnetic field made here would cause this to come in even faster, which would cause even more magnetic field, which would cause that to come even faster, which is going to make more magnetic field. It would just be this like infinite loop here where move a magnet near a coil and it's just going to, end up with an infinite amount of energy coming out of it. It would just be a continuous feedback loop. So just to the story, the end result here is that the induced magnetic field must oppose the changing magnetic field that caused that induced magnetic field. Okay, so that's Lenz's law. It says that when a magnetic field in the region of a conductor changes, electron flow is induced, right? So that the magnetic field caused by the induced electron flow opposes the magnetic field change that caused the flow. Okay, and this paragraph is just about the idea of conservation of energy. You can't have all free energy coming out of a system, right? So it's because of basically friction. Everything's dirty. You're going to feel resistance in a situation like that, and you'll see exactly that in the video coming up soon after we get to Lenz's law. But just to show the basics of it here, coil of wire and a magnet coming up here. Wire, magnet. There we go. So here we go. If you look close here, you can see this wire from the red connection here comes in and goes around this way. So it's going like that, this in the coil. And I've got a north end of the magnet here. You can see it repels the north end of the compass away. So when I bring the north in here, that's going to make the coil of wire have electrons flow, and they're going to flow in such a way that they're going to induce the north that's going to oppose that north by Lenz's law, right? It's coming in. So electrons are going to have to flow this way in order to make a north like that. Just show you here. North is going to oppose that north. That's Lenz's law. Okay. Really, conservation of energy. You can't have a magnetic field that makes it happen more. It's going to oppose its friction. So if I bring that north in, electrons are going to flow. They're going to come out of this wire into here, which is going to make this needle flow in the positive direction in here. Okay, the electrons are going the way they're supposed to, basically. So you get that. And you have the positive, boom. These electrons. See that there? Okay. Watch the needle here going the way they're supposed to, basically. So you get that. Oh, way over there. The positive, boom. Deflection of that needle. I'll do it again. I'll point out too, when I pull the magnet away, you'll see that the needle deflect the other way, because it's going to make a south that's going to try and keep that from going away. And so electrons have to go the other way. So again, opposing the motion, right? Opposing the motion of the magnet. Electrons making a north that opposes, making a south that opposes, making a north that pushes against, making a south that pulls against to try and stop the movement away. So that's electromagnetic induction, and with Lenz's law as part of the analysis. And there's weird little devices like this shaker flashlight has a magnet here with a coil of wire around it. And literally, you can shake this thing back and forth. The magnet goes back and forth, makes pulses of electrons flowing, which is energy. And so there's actually a little battery inside there, but to build up that charge. But if you flip the switch on and as you shake it, each time you shake it, the light flashes. So the energy from the electricity that's induced gets used by the light. Excuse me. Faraday actually used an iron ring as he was looking at this stuff, and so he would connect. He found if he connected the voltage here, that would make a magnetic field on this wire, which would make this become a magnetic field, and at that point, the needle would deflect. So he was looking at that kind of a setup in his actual apparatus. Yeah, so Lenz's law allowed us to analyze that stuff really easily. So again, here, if we've got a north that's coming in, picture there being electrons flowing this way. This is flow of positives, because my left hand was saying north would be on this side. So instead, use your right hand for current, I, the official current definition. Anyways, right hand, curl your fingers up in the front and down in the back. Your right hand points the thumb to the left to oppose that motion coming in, as we've already talked about. So that should make sense. You can also analyze based on the actual current flow, like if you had current flow into the page right here, the cross section of that wire, you'd have this magnetic field that goes around, as we know from the original electromagnetic induction stuff we know. So that would make it north pointing towards, and over here it's the other ways, and so on. You can analyze out individual, magnetic fields from each part of the coiled conductor, but using, again, the idea of this being a coil and using the coiled hand rule. It's just a little simpler instead of having to analyze two or a whole bunch of really spots of straight conductors. So this is based on the hand rule for a straight current carrying conductor. A little cross section of it there. So a neat demonstration to do with this. I'll show you here. Lenz's law.
All right, I'm going to demonstrate Lenz's law here. We've got a copper pipe. We've got two cylinders. One's magnetic, one's not. So that one's magnetic, that one's not. I will drop the non-magnetic one through, and you see it goes quite quickly, except that it got a vibration mode that time.
Sometimes it just jiggles as it goes through, and friction slows it down. The next two drops, it goes really fast.
Vibration mode that time.
Oh,
so
drops
fast, like it's supposed to be fast, right? So just dropping like normal, same as if I dropped like that. And then the magnetic one, you'll see what's going to happen here. You have a north coming in, so there's a magnetic field changing in the region of this conductor. That means it's going to be electromagnetic induction. So there's going to be a north that opposes it. So
there's going to be electrons flowing to create a north that opposes it, as per Lenz's law.
The north coming in, that would be electrons flowing around and around like that, maybe the north that opposes it. That north opposing is going to push, like repel, right? It's going to push against that north that's coming in and slow it down. So look at how slow it goes. Crazy how slow it goes.
So, yeah, pretty neat. A professor in university described it as the first time they saw that actually happen. They almost fell off their chair. They're kind of surprised at how much it slows it down, right? So that's what's going on, right? So like I said, this usually I show this as like, okay, that's the theory, it'll slow it down. Well, how much of an effect is there? It's actually quite an effect. You're trying to show this to someone, this needs to be like a non-magnetic material, like copper or aluminum, things like that will work. Obviously, if you tried to do this with a steel pipe, the magnet would just stick to it. Wouldn't be a fun day. They show if you took a copper pipe, I should try this sometime, took a copper pipe and ground a slit in it. And so if you had a copper pipe with a bunch of slits in it, the magnet would drop through quite quickly because the current wouldn't be able to set up and make that magnetic field that opposes. So yeah, just a way to sort of verify the logic that we're talking about. A link to this stuff, magnetic braking. So not magnetic braking. We're talking about, there's people on Facebook drive me crazy with their spelling of, they talk about their brakes in their car and they spell it like this. But anyways, we're talking about magnetic braking, like slowing down. So electromagnetic braking coming at you here. So that's up here.
All right, here's a model of electromagnetic braking. So using electromagnetic induction to cause an object to slow down. So like the drop zone, Canada's Wonderland, things like that. So we have,
you'll see that in a second.
Have an aluminum plate here that's not going to stick to these magnets. We've got a north magnet and a south. And so as this comes in here, there's going to be a new magnetic north and south above and below. And so electrons, that's a new magnetic field. And so you're going to have electron flow in this aluminum so that it makes a north to oppose that new north that happened. So in order to have that, there's basically the electrons in the aluminum are actually going to swirl around like little eddy currents. They're going to make a north that faces up. Well, that's going to oppose, say the north opposing this north here, it's going to try and slow it down. And of course, as Lenz's law says, and conservation of energy logically says, the new magnetic field that's produced would oppose the magnetic force, magnetic field that was changing. So try and give the part a push, and it stops as soon as it gets into that area, slows right down. Right? You can see it curving to the left using the braking effect. And so you can actually feel it too here, that there's a resistance force. You can actually feel that magnetic resistance force caused by the current in the plate.
It's like there's drag. It's like the brakes are on. Really, you're trying to move it back and forth, and it's harder to do than when it's just freewheeling on the cart. So things like the drop zone and Canada's Airline, they use this as a big part of the braking, right? Because instead of having like mechanical brakes that could fail at any point in time, and that would be a bad day for someone, they have this magnetic braking that just always works, right? This would never stop being, it would never stop slowing this cart down, right? It just perpetually works forever. And so questions like this you can easily analyze through. It says determine the direction of induced magnetic field for the apparatus. So if you pull this, they're showing pulling this away, which means that we'd have a magnetic field induced here that would create a magnetic field here that would try to oppose that pull away. And so in there would have to be a south. Okay, so you could write that in. I'll write it in here to show, but this is a south that gets induced and a north on that end. And then you could go along to say, okay, well, what direction would electrons be going to make that happen? So by the left-hand rule, I would have to have my fingers curling, my thumb pointing to the left, obviously, for the north, and then that would force my fingers to be curling down in front. And so this wire on this side that has the wire there, that would have to be electrons going down and out there. And so if we're talking about current, then we'd list that as the opposite way. This is electron flow, this would be current. I always like to put it in quotes because it's kind of ridiculous that we still pretend that positives are flowing. But there's the north, there's the south that I already wrote in. I was thinking that probably said current flow there, but yeah, the induced magnetic field would work to oppose the motion and so on, right? So those kind of questions are very doable, and yeah. Or based on the induced magnetic field, which way would the magnet? Oh yeah, it's the same. You could do this question the reverse way, right? If this is the induced magnetic field, you'd be able to figure out that the magnet is being pulled away because this is opposing that motion. If this was a north, right? If this was a north-south, then you'd be able to say, oh, well, the magnet would be coming in, and then this north would be opposing it, right? And obviously, each of these questions can ask about direction of electron flow as well, right? So these are all just redundant at that point. And yeah. So the reversibility of science principles leads to lots of discoveries, right? It automatically, Faraday started to look for that, right? You're like, wait a minute, if magnetism, electricity can make magnetism, the opposite might be true, and went and looked for it. And so if you have electricity that turns a motor, well, then physically turning a motor is quite likely to do the opposite, right? It's to make electricity, and that's exactly what happens. So my previous slides, diagrams to do with being a motor, like if you're applying a voltage here, it would make this thing turn. Instead, if you physically turn it, then, for example, if I'm pulling this away from this north, you picture there being an electric field, or a magnetic field, sorry, electron flow induced to make a magnetic field that's going to oppose this change. And so if you're opposing a north going away from this, you'd make a south, right? So electrons would be induced to make a south on this end. Okay, so this slide shows all that stuff, right? So you're going to make a south here that's going to resist that, or like that north receding away. So your left-hand rule could show, okay, you're going to have electrons flowing that way. So your thumb points to this end, making the north there, the south there, and so on. Really, this is a diagram of a motor being used as a generator, right? So easy, really, if you think about it, if you get these stuff that we've seen before. And there's devices just like that. This one here was a very awkward, not commercially scalable, not very popular, but it works. It makes little pulses of light. This kind was sold at Costco for a little while there. I still have one kicking around. You used to be able to it has a wind-up thing on the back of it. You crank it, so a lot of people have seen these. But basically inside of there's a motor, and you just crank it with a handle, and it generates electricity. So as you turn the handle, the light comes on, or there's even a radio, and so on. And it had at one point a battery in it that you could charge by cranking the handle. That doesn't really work anymore. The battery's not functional anymore. But yeah, but you can picture there being an electric motor in there that you're just turning by hand to generate electricity. On YouTube, I watch videos about off-road and fabrication in that. I mentioned that I bought a welder recently in that. I'm just trying to, it's fun. So these guys are pretty awesome. They were on a road trip, and this guy's, like-minded like me, where he's like understands physics and engineering principles and so on. So they had fans, and so he put a fan out the window and used it as a generator and powered another fan. So he had two fans, one working as a one working as a generator and one working as a motor. In the video, they talk about it's free power. It's like, well, it's not really free because you're creating extra drag, right? So the engine's going to work harder, but it seems free because hardly any effect on the overall amount of energy being put out by the motor, of course. But give it a watch if you're curious. It's kind of neat. You can show someone sometime. You have two fans, drive along the highway. Use one as a generator. It's kind of cool. Regenerative braking in cars is very similar to this, of course. These electric motors driving the wheels in electric cars. So then, to slow down, you can just basically make the wheels turn the motor, and that's going to generate electricity, and then the electricity feeds back into the battery. Okay, they have real brakes of normal friction brakes as well, of course, for if needed, but they can do most of their braking by electromagnetic braking, using the motor as a generator, which causes resistance and it slows you down. So the generator effect we can really analyze very easily. So if you have a wire moving your magnet, okay, so that's the idea here is you have these wires are spinning, you have magnets and so on, right? So if you have a wire moving your magnet, then we can analyze what would happen. So if we have a situation where there's electrons moving in a magnetic field, right? So it's going to induce electron flow that's going to make a magnetic field that's going to oppose the change, right? So there's going to be a flash. See, I could analyze that way. I'm not going to. I changed my mind. So let's just think about it simple here, where we have electrons going up. So thumb points up. Our fingers extend from north to south, and you literally end up with that motor force push on the electrons, right? So you have a motor force push on the electrons. They're going to get pushed this way. They get pushed this way. Okay. I had the webcam showing. I think I have a diagram here, though. There we go. Yeah. So electrons are flowing up simply by moving this wire up. And then the push on the electrons is this way, and it literally causes electrons to flow. Okay. Could analyze, like I said, the kind of magnetic field you get and how it would oppose the north here and so on. But it was just kind of easier in this case to analyze based on the hand rule that we already know. So it's if you go on in electronics and electrical engineering and that, you'll soon know or learn or hear that voltage has another name. Voltage, when we're talking about this push on the electrons, that's what batteries do, right? Batteries have voltage. Voltage and EMF, or electromotive force, are synonyms, whatever you call them. Like they're the same. They're the same thing. And so electromotive force is proportional to the amount of magnetic field there is, proportional to the velocity of the electron flow, proportional to the length of the wire. This is an analysis here. We could say, okay, this makes sense where we have a proportionality constant. We have the amount of electromotive force is proportional to these things. And so if you look at the units for these things, this is field strength. So this is newtons per, so force. And you have your speed, meters per second. You have your length in meters. So if you look at the units for all this, it works out to be joules. Newton meters is joules, and Q is coulombs. It literally is joules per coulomb, which hopefully you learned well in grade 9, that voltage is really energy per charge, right? Both batteries give groups of electrons called coulomb electrons energy to go through and deliver to loads, right? So the concept of electromotive force here, the electric force that's on, or the magnetic force really that's on these electrons, you can deduce that really that's the equivalent of voltage. So I didn't go over I didn't go over all of the details here, but like especially the units to do with the field strength. But it's true, it works. Okay. Newton meters we did in the course, which is works. That switched to be joules, and So most of that's covered in detail. I just skipped over the field strength part a little bit to be transparent here. And then, so the Lenz's law has a neat effect where if you have a superconductor, the electrons that flow in here to make a magnetic field that opposes the other magnetic field, like if this superconductor were to try to approach, like fall towards this magnetic north-south down here, then electrons would flow to make a magnetic field that's going to oppose that new magnetic field that's coming into this region of this conductor. The square thing is the conductor, right? And so electrons are able to do this without resistance, and so they're able to make a force that actually successfully opposes that force, and it literally just levitates. So superconductor levitation. Show here. I think if I just type in LED, it's searched up here. So this video shows this is actually the magnet in this case. Superconductors in here getting cooled off to minus whatever. And so it might have been the other way around. It doesn't really matter which is which. So in order for the magnet to fall towards the superconductor, it would have to approach, the magnetic field would have to change in the region of this conductor, so electrons flow to make a magnetic field that opposes it, and there's no resistance, and so it actually is able to oppose it. So it literally just holds it up. And then they show even you can pick up the magnet, and the superconductor comes with it, because again, in order for the magnet to move away from the conductor, well, that would mean the magnetic field would have to decrease here. And so it's going to make a magnetic field to oppose that decrease. So if this is a north, it's going to make a south to try to attract it, to oppose that change, right? And so that's just fun with superconductors. There's some other neat fun to do with superconductors. Here. Wow, that was loud. Apologies. So they call it quantum locking or quantum trapping, but it's because there's an aspect of quantum mechanics to do with this idea, but you can put it anywhere you want and it kind of just stays there. And again, in order to tilt it, you have to increase the magnetic field in this region if you're going to tilt it towards it. And so electrons flow to make a force that opposes it, but you're forcing it to go there. And then after that, it's just going to stay wherever it is because of the currents that are flowing, right, to oppose and hold things in place. And so you can actually, like lots of neat things, it's going to stay there. And then they have a little track. This is the coolest. They have a little track of magnets. And the thing that's flying around there isn't a flying saucer. It's not a UFO. It's not aliens. It's just a superconductor. You can tell it's all frosty because they've got it super cold. And so it can't fall towards these magnets because there's electrons flowing in here without resistance opposing that change in that magnetic field. But it doesn't matter whether they're next to these magnets or these magnets, and so it freely flows along, which is just pretty cool. When I first saw this video, I so wanted to buy this and set it all up so I could play with it. Spoiler alert, I became a physics teacher because of all the fun toys. But no joke. And the last thing I'm going to show here can save your blender in the kitchen or save electric motors. Okay, so electric motors are really just a coil of wire, right? I showed you that in the previous lesson. So they have very little resistance. So when you hook up electricity, you'd think they'd overheat, short circuit, catch on fire, right? And the reason they don't is because the spinning of the coils, right, is electrons moving, right? And they're moving in a magnetic field. And so there's going to be electromotive force on them, right? This electron's going this way and a north that way, and there's going to be a push. There's going to be a push on those electrons in those coils of wire. Well, by Lenz's law, is that push going to make the electrons, they're moving already to make the motor go, right? So is that push going to make the motor go faster, or is it going to go against the flow? And of course, it's going to go against the flow because you can't have the effect cause more movement, because that would just make motors move freely on their own forever with no energy input, right? So they refer to Lenz's law saying that this push is going to be against the flow. That's voltage, right? So it's back voltage or back EMF. when an electric motor is running freely, it basically gets to the point where not basically, it gets to the point where the voltage pushes back on the applied voltage and reduces the amount of current down to a very small amount. And then the motor, if it starts to slow down, then there's not as much movement of electrons in the magnetic field. So there's not as much back voltage. And so then some voltage starts to apply to the circuit and move the electrons to make the magnetic field, to make the motor move. And then it speeds up, and then you get more electron flow. So you get more back voltage and so on. So you have this little dance back and forth between electrons getting pushed, resisted, and then not resisted as needed. But that's how electric motors work. So if you're using an electric motor and it stalls, or it's being there's so much it's such a big load on it, it's not able to turn freely, you got to change that situation. You got to make it so the electric motor can spin enough to cause enough back voltage so it doesn't allow tons of current through it and overheat. Okay, so if you have, this is just the rest of the description that I was talking about. But yeah, if the motor's jamming or not spinning well, there wouldn't be a back voltage, and so current will flow like crazy, and it'll basically short circuit and burn out. Okay, so a while ago, I heard the blender in the kitchen. My wife was, blending a cake or whatever, and the cake batter was really thick, and so the blender was struggling, like the motor was barely turning. So I came rushing over to stop the blender from burning out. I basically said, you got to have the setting a little higher, or have the beaters not as far into the batter or whatever, make it so that the motor can spin. By the time I got there, there was some good like electrical burning kind of smell going on. The blender still works to this day, but yeah, it definitely wasn't good for it. It was starting to get really hot. All right, so that piece of physics knowledge can actually save your electric devices. So there you go. And yeah, that's it for that one. So that's electromagnetic induction, Lenz's law, as a nice way to analyze things. As you can tell, when I was analyzing that, it's easy to say, okay, well, the magnetic field is going to oppose things. And so that allows you to figure out which direction electron flow would be. So that's it for that. Thanks for watching. Talk to you later.